So, for example, no, design a bearing plate to distribute the reaction of this W21 by 68 beam with a span length of 15 feet 10 inches centered center of supports. The total service load including the beam weight is 9 kilopounds per foot with equal parts dead and live load. So meaning 9 kilopounds with equal parts. So divide nimo ni siya kaduha, that is the value for your dead load and live load. So the 4.5 and 4.5. Now the beam is to be supported on reinforced concrete walls with FC prime 3500 psi. With the for the beam, the yield strength of this W21 by 68 is 50 ksi, and for the plate is 36 ksi. The so first is you have to determine the factored load, no? So the critical value for the factored load that will govern in the design is 1.2 dead load plus 1.6 live load, no? So divide by 2, 4.5. This is the value of your factored load. So that the reaction, if you have the beam, no? If you have the beam, this is the W, then simply supported beam. This is the W21 by 68. Then kay uniform load, no? This is actually very basic in the theory of structures and also in your mechanics of the deformable bodies, reactions, both reactions, uniform load. So if this is W and L, the reaction is actually equal to WL over 2, no? And the reaction, this is the ultimate reaction, no? Is WL over 2. So that is 12.6 divided times the length. So to convert this one to feet, since this is feet, 15.83 divided by 2. So this is the maximum, reaction, no? In this one. So this part here sa, or in here, nana siya plate, no? To connect to column, to transfer the load. If this, ako ato na siya para ko, if you try to say na kay plate diri, this is the beam, no? This is the wide flange, W21 by 68. So we are required to design the base plate. This one kana siya. So determine the length of bearing to prevent the web yielding, di ba? So remember the procedure or the steps, no, in designing the bearing plate. First is we have to determine the dimension L sub B so that these limit states, web yielding and web crippling are prevented, no? So first is we will try to solve, no, with regards to web yielding and web crippling. Then we'll try to determine this bearing length, then determine the value of your bearing base length, and lastly is the thickness, no, with regards to limit state bending strength. All right, well, this one, no? So to determine the bearing length L sub B, the nominal strength ganina is this one, di ba? Try to look at, since at the support, naman siya at the support, try to balik, no? This one. Yes. This one, no? The nominal strength at the support is this value. A yield strength times thickness of the web times 2.5K plus L sub B. Then, okay. Diri ta answer sa, okay, wala magud na sayop. So, diri ta sa book, no? Of Sigoy. Maora man siya. So, this is the nominal strength, no? For the design strength greater than or equal to the ultimate due to the factored load, no? So, for the web yielding, no, your resistance factor is 1.0. Then, substitute or 1.0 times the yield strength for the beam, no, which is 50K SI times the thickness of the web of the beam. So if you try to look at the section properties table, makita niyo siya that is table 1-1. So the thickness is, this is from the table, no? This is from the table, from the AASC manual. This is table, from the table 1-1 in the AASC manual. Times 2.5, the value of K. Alright. K is actually from the table also. No? The problem, the beam is W21 by 68. W21 by 68. For the purpose of computation, actually there are two values of K. There is the design dimension and the detailing dimension. But for the purpose of computation, we will select the value from the detailing. I mean, not from the design dimension. From the design dimension. So, say, we'll try to look at this beam in the table. That is W 21 by 68. W 21 by 68. This one, no? By 68. W 21 by 68. Sorry. W 21 by 68. Try to look at that one. There are actually two values now of the K design and K detail. So for the purpose of computation, we will select always for the computation the K design, and the value for the thickness of the web is 0.43, no, this one 0.43, and the K, which is in the formula, K is 1.19, then is greater than or equal to this one, the reaction at the support, 99.73. So we'll try to find the value of L sub B, so that the resulting bearing length is 1.166. Okay, I already said this one earlier. Note that two values of K are given in dimensions and properties tables. No, a decimal value called the design dimension and a fractional value called the detailing dimension. We always use the design dimension in calculations. No, for the value of K, use the ASC equation J10-5 to determine the value of L sub B required to prevent web crippling. So ganina is for the limit state web yielding. Now we'll try to solve the value of L sub B with regards to web crippling, as far as web crippling is concerned, no? Ano siya? So we assume that first is we assume that actually there are two equations, di ba? Ganina, sorry. Sa lecture note na to. Sa ganina, naatay two equation for as far as web crippling is concerned. This one, no? So first is in the example, first is we'll try to select this condition so that we can use this nominal strength, no? So kana siya, assume that the bearing length, the ratio of the bearing length and the depth of the beam is greater than 0.2, and we try the second form of the equation itong ganina. For this one, so remember for the web crippling, the resistance factor is 0.75, and substituting the equation, no, the whole equation, this one, no, this one, to the r sub n, no, because of this concept of the design strength. So substituting this one value so that only L sub B is unknown, because this TW, this is we can find this one in the table. We can find this one in the table, TW, and this the thickness of the web and the thickness of the flange. Makita natin ni siya. Square root of E, this is the modulus of elasticity of steel, which is 29,000 KSI, times the yield strength of the beam, no? 50 times the thickness of the flange. Now, this is also from the table. You can find this one in the table. And thickness of the web, no? Which is we found earlier in the table, 0.43. Greater than or equal to the 99.73, which we computed due to the applied uniform loads, di ba? Due to dead load and live load. So, muna siya. So that only L sub B is unknown, no? So, manipulating this one by your calculator, your L sub B is 3.0 inches. Then, we check our assumption, di ba? Ganina, nag-assume ta that we first assume the second condition, no? The L sub B over D, which is greater than 0.2. So, we check if our assumption is correct. So, we got the length of the bearing, which is equal to 3.0. So, to check the assumption is this one. If it is true that uh, greater than ba siya sa 0.2, di ba? This one, no? This second assumption, kung greater than ba siya 0.2. But from the table, the depth of the shape, the W21 by 68, the depth is 21.1. This is from the table. So the value is 0.2, which is less than 0.2. So our assumption is wrong. Diba? We assume this one, our assumption is should be greater than 0.2. But we end up less than 0.2. So not good, no? Then we consider the first condition. Katong this one. The first formula or equation for the nominal strength, no? This bearing length, the ratio of bearing length to the depth of the beam is less than or equal to 0.2, no? So, substituting this whole formula, this whole formula in the R sub n, and again, using the resistance factor 0.75 for the web crippling, no? Lahi-lahi man siya. Web yielding, web crippling, lahi-lahi siya of resistance factor and also the factor safety for ASD solution. So, using this condition, no? And so that the L sub B is the only unknown, no? This is from the table, this from the table, this one table. for the W21 by 68. Also this one, no? You have this value, this one. And again, the value for the ultimate load from the loads, no? Applied loads is 99.73, which we computed earlier, no? The reaction, this is the ultimate, no, reaction, no, at the support. So that L sub B is this value, 2.59. And we check our assumption, yeah? Our second assumption. Our assumption is that this one, second assumption, because the first assumption is not good. So this one, no, assumption. If it's really less than 0.2, and we found out that it is really less than 0.2. So this is okay. No, this one. Then we try the value. So in here, the 0.6. All right. We try the value, no, for the bearing length 6 inches. Then determine dimension of B from a consideration of bearing strength. If we conservatively assume that the full area of the support is used, the required bearing area A sub 1 can be found as follows. So if the full area of the support is used, we follow this value of your nominal strength, no, for design of for the bearing strength. This P sub P is equal to 0.85 FC prime A1. Kanina, di ba? This one here, this here. If the full area of the support covers, if the plate covers the full area of the support, so we'll use this one, no? Then for the bearing strength limit state, the resistance factor is 0.65, di ba? Times the 0.85 FC prime, that is 3,500, 3.5, area of the bearing plate greater than or equal to 51.57 inch square. Is it indicated in the problem na full dapat? Oops. Wala siya, no? But in here, so in here, yes, we conservatively assume, no? We have here, we conservatively assume that the plate covers the full area of the support. For example, the column, no? Then, this is actually the reaction, no? Which we computed earlier, 99.73. So that we get the area as 51.57 square inches. So the minimum value of dimension B is using the assumed value of the bearing length, which is 6 inches. So this one divided by the 6 inches, no, to get the value of B equal to 8.6 inches. So the flange width, no, but the flange width from the table, this is from the table 1-1, this is actually flange width, no, 8.7, making the plate is slightly wider than the flange, which is okay, no? which is desirable. Yes, desirable. So rounding up, we try B equal to 10 inches. No? Yeah, compute the required thickness, plate thickness. First is we have to get the value of N, no? Which is, this is actually the cantilever length, no? Katong uniform load at the support, uniform load at the support, itong ganina. So that is equal to B minus 2K over 2, no? Then we try this 10 inches value for B, 10 minus 2 times the value of K. This is from the table, no? The data, this is the design value for K, no? Which is 1.19 divided by 2. So the value of N is 3.81 inches. So from this equation, thickness is equal to square root of, yes, we discussed this one, no? The value, the formula for the thickness is square root of 2.22 times the ultimate reaction at the support times N squared over B, Elsa B, Fy. So that the value of thickness is 1.22 inch. Or we could use 1 1/4 thickness times, this is the plate, no? Use the plate, this is thickness, this is the Elsa B, this is the B, no? Or use this 1/4 by 6 by 10 dimension of the plate. Alright. Elsa B should be greater than 3 inches, greater than 2.59 inches, no? Then we try 6 inches. We try 6 inches, Elsa B. Okay, 6 inches. Because for the first limit state for the uh, web yielding, your Elsa B should be greater than 1.66 inches. 1.6 inch. And for the web crippling, your Elsa B should be greater than 2.59 inches. So that we try the Elsa B, taho kay ba? 6 inches, no? Nga na siya. Then, follow these steps, no? For the design. Then we end up this property for the plate, no? The thickness 1 1/4 by 6 by 10 inches plate. This is LRFD. For ASD, actually, the same naman siya, no? It's just that the load combination is, you only have to add the dead load and the live load. Then again, the same procedure for the LRFD, no? And so that the value, the same answer also. For the ASD solution, we get the same answer. Use the plate. No, not the same answer. This is actually bigger because the thickness is 1 1/2 by 6 by 10. Different from LRFD. No? Conservative. The value for LRFD is more conservative than ASD. But the process is actually the same, no? Will not, ako mo na lang, kung ano, no? Try to understand, no? For the ASD solution, the same procedure, it's just that the the combination load combination, no, is you only have to add the live load. Then the same procedure for the LRFD, right? So this is the last topic for the beam. Then next is we'll discuss the beam column. No, beam column. I think that will be the last chapter that before this semester ends, because final exam term is next week. So that's all, and thank you.